Hi everyone, my name is Alec Moore, and I'm in the XRT, Extended Reality and Training lab at the University of Central Florida. I'm presenting our workshop paper, A Formative Evaluation Methodology for VR Training Simulations. I'm going to discuss our formative evaluation methodology and our experience with a case study using the methodology. So, our methodology, CARI, is a novel formative evaluation methodology for training scenarios that couples with the UX design lifecycle. It involves the following set of steps: capturing subject matter experts performing the real-world task, automating data logging for subtask performance metrics, running a rigorous user study, analyzing subtask performance, and then finally inspecting the software and hardware to identify subtask usability issues. While CARI is designed to be used throughout the UX design lifecycle, it can be implemented throughout at any point. We ourselves didn't make use of it until later in our design process, but because we had captured video of the procedure early on, we were able to use it for our subtasks and analyses. This video artifact allowed us to fully identify the necessary subtasks to successfully perform the training task. Here, you can see a list of the 20 implemented subtasks, what type of interaction they necessitate, and the amount of time it took for the subject matter expert to complete them respectively. Our discussions with the subject matter experts, the video, and the requirements helped drive our design. Knowing what types of interactions were necessary, we implemented a green, semi-transparent interaction queue for virtual hand interactions, and walking and looking warranted respective icons. Integrating the data logging for the automate stage was relatively non-difficult. For each subtask, we record the time in seconds for our user to complete it. This time is measured from the conclusion of the intro, once the user is expected to act, until the user has performed the interaction required to complete the subtask, like this example where the user must select a dialogue option.
We need to press the power button on any of the machines to turn off the system.
Alright, I'll press the power button and turn it off.
In addition to subtask time, we also record any errors performed during the subtask, such as selecting the wrong dialogue option, as well as whenever the patient breaks sterility at any time throughout the procedure. Depending on the training task, there may be other salient values to record. We logged our values per subtask in a CSV file for our later analyses. After setting up our automated data logging, we ran our rigorous user study, based on the application as it existed after significant feedback and demos with subject matter experts. We treated our independent variable as the subtask completed, which is for our repeated measures ANOVA that we conduct later in the analysis stage, and our dependent variables were the collected subtask metrics, as well as the responses to the questionnaires that were administered after the conclusion of the training scenario. We also considered the knowledge post-test. Our materials were the HTC Vive, the application itself which was built in Unity, and the SteamVR plugin for handling user input. The procedure was simply an informed consent followed by background survey, then the SteamVR tutorial to familiarize participants with VR, then the application itself, followed by the questionnaires and knowledge post-test. We had 20 participants, 4 female, at a mean age of 23.6 years old, 12 of whom had prior VR experience. So now, in the analyze stage, we're looking at the results of our per subtask metrics. We can't directly compare among completion times because the interactions involved in each subtask can vary widely. So we looked at using the subject matter expert times for thresholds. Originally, we anticipated comparing the participants' time to 2, 3, or 4 times the subject matter experts to determine if they succeeded or not, but we found that comparing directly to the SME's time worked best. This may be in part because the SME was aware of the recording and likely adjusted the time to complete each subtask accordingly for clarity, but in general, we anticipate comparison to values proportional to the SME time to be helpful. Additionally, we initially expected the mean number of errors to be useful to identify subpart subtasks, but found no significant results. Looking at the percentage of participants who completed the subtask without errors, however, yielded one subtask that participants had particular difficulty completing without errors. With these values, we had determined 5 subtasks to inspect for issues. The first subtask to investigate is number 2, consulting the surgeon. Originally, we had decided on displaying two different dialog windows that show up based on whether you're looking at the surgeon or the staff more in an attempt to reduce clutter. We determined, however, that this made it difficult for participants to know that they had specific dialogue for the surgeon, and so we've reversed that design decision, and now we display both dialog menus simultaneously when looking at either virtual agent. The next subtask that warranted further inspection is subtask number 7, Hold the Instrument Carriage. This is the first interaction that requires the use of both hands, and what we determined is that it wasn't clear immediately that the interaction cue animation originates from the hand that's not currently holding the wrench. Oftentimes, the user's hands would be held slightly outside of the field of view, so the user wouldn't see that it's coming from the other controller. To ameliorate this issue, we decided to incorporate hand models into the cues to do a better job of conveying handedness. The next one to inspect is subtask number 9, Rotating the Wrench. After inserting the wrench, the virtual agents would be talking, first to affirm that inserting the wrench was correct, then to introduce the next subtask, which was to turn the wrench 90 degrees. Generally, the mention of 90 degrees counterclockwise occurred before finishing the introduction, and the participant would immediately turn the wrench. This turn, however, wouldn't be registered by the system because it was determining that start angle at the conclusion of the introduction to the subtask. So what would happen is the participant would turn the wrench, then it would record that orientation as the start angle, and then they would be required to turn it a further 90 degrees. In some cases, this would seem to be around 180 degrees in total. Because of this, we're modifying our system so that it sets the start angle immediately upon insertion. For subtask 12, we determined the presence of a subtle bug in the interaction queue. In this interaction queue, there was a transparent hint object that would present itself statically relative to the instrument. Thus, pulling the instrument out would make it move, giving it the appearance of being correctly animated, as you can see in the top video. We fixed this by implementing the correct, consistent interaction queue, as you see in the lower video. Finally, subtask number 17, using the cannula lever, we identified a few aspects that made this interaction unique. The target of this selection is often visually obfuscated, and the collision volume is the smallest of any in the scene. To improve participants' ability to perform this subtask, we're making a few changes, including providing a walking component to reposition the participant where the lever is less obstructed. We're also increasing the size of the collider and using a vote technique with closest intersection-based disambiguation to handle potential issues with multiple intersections. As you can see, there are multiple selections that may be made when attempting to select the cannula lever, so the use of a disambiguation technique is important. Thank you for your time. Once again, my name is Alec Moore, and I'd like to thank my co-authors, as well as the University of Texas at Dallas, where this research was conducted. I should be available for any questions. Again, thanks.